welcome to the series on noise control in mechanical systems with me, Professor Sneha Singh from the Indian Institute of Technology, Roorkee. And in today's lecture, we will discuss about one type of resonating sound absorber which is called as the Helmholtz resonator. So, to quickly summarize, we are looking into the module of passive noise control, and within that we are looking into the various kind of acoustic materials which can be used for sound control, and one type of material are the absorbers, and within that we have one type of absorber known as the Helmholtz resonator that we will be discussing in today's lecture. So, the introduction to Helmholtz resonator, the working principle, the resonant frequency, the advantages and limitations, and the various applications of this resonator will be discussed. So, what is Helmholtz resonator? This is a kind of, as the name suggests, resonator, which means that it is some kind of structural element which undergoes resonance at some predefined frequencies, and due to the phenomenon of resonance it is able to absorb the sound. It was proposed by the scientist Hermann H.F. von Helmholtz and it is named after him. So, this is a sound absorber. It consists of an acoustical cavity which is confined within some rigid material or some rigid boundaries, and then it is connected to the exterior environment by a small opening called as the neck. Okay. So, it looks something like this. You have some kind of acoustical cavity. It can be of any shape, it can be rectangular in nature, cuboidal in nature, it could be cylindrical in nature, spherical nature. So, any kind of acoustical cavity of any shape, and this capital V becomes the volume of the acoustical cavity which is confined within rigid boundaries. So, the boundaries have to be rigid. Okay. This is the rigid boundary within which this acoustical cavity is. It contains acoustic medium. The most common medium which is used for Helmholtz resonator is our air. So, usually it contains the confined acoustic medium, most likely air, and this cavity is being connected to the outside world through some kind of extended opening which is smaller in kind of cross sectional area and has a length or an extension called as the length or the neck length. So, this is called as the neck of the Helmholtz resonator. The diameter becomes twice of r, where r is the radius of the neck, L becomes the length of this neck, so which is connecting the cavity to the outside environment, and V becomes the volume. So, this is your typical Helmholtz resonator. Now, this will act as an absorber. So, the first condition for that is that the volume of the acoustical cavity has to be much smaller compared to the cube of the wavelength, or there, in other words, I can say that all dimensions of the Helmholtz resonator, so be it the length of the neck, the diameter of the neck, or the dimensions of the cavity. So, all dimensions of this Helmholtz resonator, they have to be smaller than the wavelength under consideration, so that it can act as an absorber at that wavelength. This becomes a generic condition for Helmholtz resonator to act as an absorber at lambda wavelength of the sound wave. So, let us see what is the working principle of this particular resonator. So, what happens is that here you have the incident sound waves, they are hitting. So, from the outside environment, suppose there is some noise source which is creating these pressure fluctuations or sound waves which hit the neck, and when they hit the neck, they can create vibrations in the molecules of the neck. Okay. So, whatever air molecules are there, so when they hit it, they create vibrations or the back and forth motion of the air particles in the neck, but here the neck is being connected to a confined air cavity, right. So, it is connected by rigid walls. So, the air by default, it is a compressible medium, and it has a resistance to compression. okay, and similarly it has its own resistance to expansion. So when the sound waves, they are hitting the neck, they are vibrating the air molecules in the neck, which in turn is trying to, as the molecules in the, as the vibrations or the fluctuations of the air particles, they reach through the neck into the cavity, these vibrations, they tend to sort of compress the air molecules within the cavity and expand it. So the vibrations essentially, they try to compress and expand the air molecules within the confined cavity, but because the air molecule is confined, it has no way to get around. If suppose the cavity, there was no confined cavity or there was no rigid boundaries, then whatever these vibrations were, they would pass through, as the particles are compressing and expanding, they would have other spaces to fill and there wouldn't be that level of resistance. But here the air molecules within the cavity, they have nowhere to go. So when the air particles from the neck, which are vibrating back and forth, are hitting and trying to hit and compress the air particles in the cavity, they have nowhere to go, and when they try to expand, again they have nowhere to go, and therefore they create a little bit of resistance because they have nowhere to, they have no spaces to fill. Suppose some expansion happens or contraction like that. So in that case, so these confined, the molecules within the confined cavity, they have their own resistance to compression and expansion, and this becomes like their inherent stiffness. So they act like an oscillator. Okay, you can think of a mass spring system, a typical mass spring oscillator. So in the field of vibrations, you come across various oscillators where we have a mass spring system. What is it? You have a rigid boundary connecting one end of the spring, and on the other end of the spring you have got some mass which is free to fluctuate. So when you push the mass of the spring, if you look at this figure here, what you do is you are trying to, let's say, push the mass using this. Suppose you are applying the force and trying to push the mass in this direction. What will happen? Due to the spring force has its own stiffness, it has resistance to expansion and contraction. So the spring force will act in the opposite direction to restore to its original motion. And in the same way, suppose you had applied the force and tried to contract it in this way, then the spring force will again act in the opposite direction and try to restore the spring back to its original length. And this is how, if you suppose stretch a spring with a mass and just leave it, it sets into vibration or oscillatory motion. So here also this particular Helmholtz resonator acts like a mass spring oscillator. Here the air particles in the neck of the cavity. So all the air particles present here in the neck and the mass of them, because these are the molecules which are vibrating back and forth, and their vibration of back and forth is being resisted by the compressed cavity inside this confined, so the compressed air molecules in the confined cavity. So these are trying to vibrate back and forth, and this is acting as the resistance to their expansion and contraction. So the mass becomes these masses of the air molecules in the neck which are vibrating back and forth, and they are being resisted by the compressibility or the bulk modulus of the air within the cavity. So their motion is being opposed by the bulk modulus of the air within the cavity of the resonator. So that acts as your spring element. So this becomes the mass, and this bulk modulus of the air within the cavity, which is resisting the expansion and contraction due to which is being initiated by this back and forth motion. So this becomes your spring which is trying to resist the motion, and hence oscillatory motion is set. So this overall system behaves as a mass spring oscillator, which means it behaves as a kind of oscillator, and it has its own unique fundamental frequency. So owing to, so for example, in this spring system, the natural frequency of this mass spring oscillator is root of k by m. So, in the same way we have suppose a Helmholtz resonator where the spring constant is simply because of the bulk modulus in the cavity. So, depending on what is the volume of the cavity, okay, and what is the medium considered, you will have a certain bulk modulus which will become a K, for which will correspond to a certain K of the system, and the air mass would depend on then the volume of the neck. So, the length of the neck as well as the surface area of the neck will determine the mass. So, it will have its own natural frequency. So, now that we know that the Helmholtz resonator, it acts as a mass spring oscillator, and it has got, sometimes it is also called as like an air spring oscillator, because the air element is acting as a spring. Okay. So, it is also called as an air spring oscillator, because here the confined air is acting as the spring element. So, what happens at this kind of thing, so suppose you have an incident sound wave which is at the same frequency as the fundamental frequency of this resonator, then there will be something called as the acoustical coupling. So, we have already seen what is the noise control phenomenon in a panel resonator. So, whenever the incident frequency with which the sound waves are hitting a panel absorber, if the incident frequency matches with the natural frequency of the vibration of these panels, then there is resonance, and whatever sound waves are hitting, they are being used up in driving back and forth the panel, and the energy gets dissipated. Here also in the same way, whenever the incident frequency is same as the fundamental frequency of this Helmholtz resonator, then there will be acoustic coupling. So, whatever is the incident energy, it will get dissipated in vibrating the Helmholtz resonator at very high amplitude. So, resonance will be set, and all the acoustical energy or the sound energy that actually was incident now is sort of getting absorbed inside into the absorber. Okay. All of this energy is going in and is being used up in doing work in vibrating this absorber or the molecules of the absorber. So, in a way you can say that the energy is getting absorbed and going inside this resonator. So, at the resonance, the vibrations of the air molecules in the neck, they are maximum, and this amplifies the viscous and the frictional losses due to resistance faced by these air molecules, and also whatever is the energy, it gets dissipated in doing work in vibrating this oscillator at high amplitudes. Okay. So, therefore, because the maximum dissipation happens when there is resonance, which means when the frequency of the sound wave matches with the frequency of the oscillator, then you have the maximum vibrations and hence the maximum energy dissipation. So, the sound absorption of this Helmholtz resonator, it will peak at its natural frequency. Okay. So, let us say suppose we have a particular Helmholtz resonator like this, and let us say F naught is its first or the fundamental frequency or the first natural frequency, and then we have whatever are the multiples of it where they become its higher harmonics. Okay. Because the resonator will have the frequencies in the integral multiples of F naught. So, the first frequency would be F naught, followed by F naught, 2 F naught, 3 F naught, and so on. So, here the sound absorption of this resonator should look something like this, and you have this let us say the SAC. So, wherever the resonance happens, you have maximum energy dissipation and going into the absorber. So, it should look like this, sharp peaks repeating at some intervals, and these should correspond to the natural frequencies of the resonator and its harmonics. Ideally, this should be the case, but most of the times due to other factors, the SAC may not exactly resemble this. Okay. But because the phenomenon of resonance happens at specific frequencies, which is exactly when it is matching F naught. So, only at that small unique band where f is the f incident is equal to some n times of f naught, only within those where the frequency matching is there, in that small sharp band would you get resonance, and beyond that there is no resonance. So, the characteristics would be very sharp and narrow. It will not be a broad band or a very broad range kind of absorption. It would be a narrow absorption which would be centered around the resonator's natural frequency. Okay. So, as you can see that compared to the porous fibrous materials, both the panel absorber as well as the Helmholtz resonator, they can achieve low frequency absorption, because you can tune the dimensions of the system so that the first frequency comes at a lower hertz, okay, some low frequency you get. So, you can attain natural frequency at any desired range, at any desired point, by tailoring the dimensions of the resonator, but the characteristics is going to be very sharp and narrow. So, you can only get at some specific target frequencies you can absorb, you cannot do it for a wide range. So, as you see that the absorption characteristic depends a lot on what is the fundamental frequency of the Helmholtz resonator. So, the fundamental frequency f naught, this value here of this Helmholtz resonator is given by this expression here, which is C naught by 2 pi under root of S by V into 1 plus 1.7 times R. So, this is one very important equation every noise control engineer or every student in this field must memorize it by heart. Okay? So, very important relation. C naught here is the speed of sound in whatever is the acoustic medium you are considering. In most of the cases it is air. So, it is the speed of the sound in the acoustic medium where the resonator is. Capital S is the cross sectional surface area of the neck, and capital V is the volume of the cavity which is confined, R is the radius of the neck, and capital L is the neck length. So, ideally the SSE peaks should then be obtained at the integral multiples of this fundamental frequency of the Helmholtz resonator. So, it should occur at the first fundamental frequency which is given by this expression, and then at its successive kind of multiples. Okay. So, let us say for example, this is a particular absorption characteristics of a Helmholtz resonator with these dimensions. So, if you think about it, let us find out what is the fundamental frequency of this Helmholtz resonator. We can simply write f of HR, the fundamental frequency of the Helmholtz resonator. It is C naught, let us take it as 340 at room temperature by 2 pi, and you have this S here, S by V into L plus 1.7 R. So, S is the cross sectional surface area of the neck. So, the neck radius is given assuming a cylindrical neck. If nothing is given, you assume it is a cylindrical neck. So, pi times of this pi r square should give you the cross sectional area of the neck. The volume of the cavity in the SI unit is given as this, and then within that you have L plus 1.7 R. So, the length is 7 millimeters. I am writing everything in the SI unit, the radius being okay. So, if you evaluate this expression, what you will find is that it comes close to 1100 hertz, and you can see this is the sort of absorption characteristic of this resonator measured. It always peaks. So, the peak here comes somewhere around 1200 or something in the experimental measurement. So, obviously there are some inaccuracies in manufacturing or some other most likely the inaccuracies in the manufacturing, but it is coming very close to 1100 hertz, which is the theoretical estimate of its fundamental frequency. So, you can see how the absorption characteristics are very sharp and narrow. Okay. So, suppose from this the first guess you can make is that where can we use this resonator? We can use it, suppose that we have certain machinery which has some kind of a rotating component, and it creates the sounds corresponding to the rotational frequency of that component. So, in that particular frequency and its harmonics, we are getting peaks in the sound wave of the machinery. So, when there are targeted sound peaks, okay, we know that the sound is occurring at some particular peak. So, when you have tonal sounds, tonal noise sources or noise sources corresponding primarily to a rotating component of a machinery, there the waveform, it will be peaking at certain specific frequencies and its integral multiples. So, when you have such targeted absorption, it is not a broadband kind of a sound, but it is more tonal in nature with harmonics, a very harmonic kind of a sound. Then there, when we know, we already know beforehand what are the frequencies, what are those specific values of frequencies that needs to be absorbed from the noise waveform. There we can use this resonator. We can design the dimensions of the resonator so that it absorbs the sound exactly at those frequencies. So, let us see the advantages and the disadvantages. So, advantages, it contains a single hole, it unlike porous fibrous absorber, it is much easier to maintain because there are not numerous pores and holes. So, much easier to maintain and clean. Similarly, the fibers, there are no loose fibers which will be falling down. So, again more durable and more easier to maintain and clean than the porous fibrous absorbers, but definitely they are in comparison easier to maintain and clean than the porous fibrous absorbers, but more difficult to maintain and clean compared to the panel absorbers, because in the panel absorbers you just have a stiff panel, you do not have any neck which is a sensitive area and with a small dimension or a micro hole or something. So, it is easier than porous fibrous, but difficult than panel absorber in terms of maintenance and cleaning. Then low frequency noise control is definitely possible. Okay, these are some of the advantages, and unlike the porous fibrous absorbers, they can absorb at any kind of low frequency range, and the magnitudes would be very high at the targeted low frequencies. Okay, most of the times it is almost close to unity, and it can be used for extremely selective high end noise control applications. What are the limitations? Again, although they are easier to maintain and clean than porous fibrous, but they are more difficult to clean than the panel absorbers. And the very critical limitation which really bugs the noise control engineers is that it has got extremely sharp absorption peaks. So, wide range absorption is not possible. So, this kind of limits its usage. We can only use it for those kind of sound sources where the noise is peaking at some specific frequencies. Okay, there is no broadband content in the sound, because it can only do this selective absorption, like pinpointing and doing the selective absorption at some specific frequency values. Okay, so wide range absorption is definitely not possible because of the very sharp peak, and it is expensive to construct and install in a machinery. It adds an extra volume to the machineries, and many machineries where the design of the machinery is of prime importance, which sort of dictates the function of the machinery. There it is not always possible. The designer of the machinery will not always allow you that, okay, in my machinery you can add an extra volume and create some kind of protuberance which can act as a resonator. So, not every machinery design can allow for a construction of a Helmholtz resonator. Okay, so, again limiting their usage or installation, giving an installation difficulty. So, now let us see what are the most common applications of these Helmholtz resonator. So, as I told you that again and again, this is a very highly selective low frequency absorber, okay, where you know that exactly this hertz you want to absorb. So, 150 hertz or 200 hertz, so exactly know that that is the value where the sound is peaking, and that is the value where I want to absorb. I am not concerned about absorption at a broad range, but only at these specific values, and at the low frequency range, then definitely this can act as a very good option. So, it is used in the situations where the frequencies that have to be mitigated are already known to us, and where the construction is also possible within the scope of the machinery. So, let us see, I think the most common application of a Helmholtz resonator is as within the automotive exhaust muffler. Okay. So, you have the muffler built which is built to reduce the noise from the exhaust line of an automotive. You know that the exhaust is one of the major source of automotive noise, and the mufflers or the silencers are built to reduce this exhaust noise. And the resonance, almost every, now these days there is no muffler which is built without a Helmholtz resonator. A Helmholtz resonator is there in every modern automotive exhaust muffler. So, it is very widely used in this application. So, what is the purpose? To reduce the exhaust noise. You can see here in this vehicle, the muffler is there in the tailpipe or the pathway of the exhaust. And what it does, so if you see here, so you know that the exhaust is coming out, the exhaust noise, it will depend on how the engine of the automotive is functioning. And engine is a very classical example, engine, it has its own unique cycle, okay. It has got a typical RPM at which the engine is running, and based on the RPM or the revolutions per minute, you can find out what is the cycle frequency in revolutions per second, and you would know that okay, these many times per second you would have the release of the exhaust, and these many times per second you would have the combustion happening. So, the whole operation of the IC engine within an automotive system, it is very synced with the frequency at which the engine is operating. So, here whatever noise is created because of the operations of the engine, be it the combustion noise, be it the exhaust noise or any other thing related to the engine, the waveform, the sound waveform, it will be such that the noise will be peaking at some fundamental frequency which will correspond to the frequency at which the engine is operating. So, the sound will peak at the engine frequency and its higher harmonics. Okay. So, it is a very classical example, the engine noise, whatever is the engine noise or the exhaust noise, it has a typical harmonic content, okay. It peaks at a fundamental frequency and its higher harmonics. So, that becomes the best candidate for a Helmholtz resonator to absorb. So, we can create a Helmholtz resonator whose fundamental frequency is going to match with the fundamental frequency of the exhaust noise waveform, and it will absorb those frequency components. So, this shows a typical automotive muffler. The exhaust is going into this muffler. So, this is designed to silence or reduce the exhaust noise. Okay. So, muffler is designed to reduce the automotive exhaust noise, and Helmholtz resonator is incorporated in every modern exhaust muffler. Okay, this muffler here, this is what it does. And so, the exhaust air comes in through this pipe, it passes through these perforations. So, as you can see, this is the pathway it is following. If you follow this arrow here, it goes here, then after that it comes to this cavity, then it goes here, and then finally it goes out through this way. So, this is how it follows if you follow this arrow. So, first of all, some kind of noise loss happens because it is passing through these perforations, and in the perforations there are viscous losses happening. In our next lectures, we will study about perforated panels, micro perforated panels. So, you would learn in detail how small holes, how just making some sound waves pass through these small holes can actually lead to attenuation of the sound. So, first of all, the exhaust is made to pass through these perforations and some loss is happening, and while passing they enter this cavity space. This becomes your Helmholtz resonator, and then it absorbs. So, while the exhaust air is passing, there is at the side of the pathway of the exhaust, you have the Helmholtz resonator which absorbs the various harmonics, and after passing through this it comes out. This shows the back view of a car, and you can see this kind of a muffler which has a Helmholtz resonator inbuilt within the muffler. Then other application is it's simply used to create musical tones in various kind of instruments such as the acoustic guitars. Here you can see this becomes the opening, and this is the wooden structure. This is hollow inside, right? This is hollow inside. So, this acts as confined acoustic cavity. The wooden box is the rigid boundary, and within that we have the confined acoustic cavity, and this is the opening of this cavity or the neck, and this itself is a Helmholtz resonator. So, when we are plucking the strings of the guitar, it creates the vibration motion or the oscillatory motion which hits the opening of the cavity or the neck, and then it acts as a Helmholtz resonator and it tunes with the vibrations at its resonance frequencies, which creates very tonal sounds. Okay. And in the same way, it can be used for various duct noise control. Ducts and piping systems in various industrial machineries, they carry the various kind of fluids at various temperatures. So, first of all, there is the noise due to the flow of the fluid itself, then there is a noise due to the vibrations of the pipes. So, these ducts and pipes, they are a major noise source in various kind of machineries, and what you can do is usually the Helmholtz resonator are built as a sideway in the duct system. This is a typical schematic of what happens, how a Helmholtz resonator is inbuilt into a duct. This is your duct or the pipeline, and then on the sideways you have got this protuberance or a cavity built up, which is the Helmholtz resonator, and it is used to absorb the duct noise. Here also the design is such that the fundamental frequency of the Helmholtz resonator that is built should match with the fundamental frequency of the duct. The duct is an open pipe, it will have its own fundamental frequency. So, the fundamental frequency of the duct system. So, at that frequencies the highest amount of noise will be created while the fluid is flowing through the duct. So, the noise in the duct will peak at its natural frequencies, and that should match with the fundamental frequency of the Helmholtz resonator, so that at those frequencies it can absorb the maximum sound. This shows a typical pipeline in industrial machinery, and this kind of structure is actually the Helmholtz resonator within this. Okay. So, with this I would like to close this lecture. Thank you for listening.